of a statistician during the 15 years following the award of their doctorate. And it is awarded annually by the Centre de Recherche Mathématiques and the Statistical Society of Canada. And many of the most distinguished statisticians in Canada have received this prize. And we're very happy to have today Professor Zhou Zhou from University of Toronto, who will give his presentation. And Aurélie, our colleague, will continue this introduction. Thank you very much.
So it's my pleasure to welcome you, Zhou. Dr. Zhou is a professor of statistics at the University of Toronto since 2009, where he was hired after completing his PhD at the University of Chicago. He has been awarded the 2023 CRM-SSC Research Prize for his contributions to time series analysis and non-parametric statistics. Specifically, one of Zhou's significant contributions to the field is on the analysis of non-stationary time series, a topic that he will keep exploring with us today in his talk entitled Auto-regressive approximations to non-stationary time series with applications. Thank you very much and welcome.
Thank you so much. It's my great honor and a great pleasure to come here to give this talk. Yes, so as I already just mentioned, I was actually devoting much of my time to the study of non-stationary time series. So therefore, it's a great pleasure today to share some of this work with colleagues and with researchers here. So today, what I'm going to do is that I guess a lot of audience of this talk may not be that familiar with time series analysis. So therefore, what I would do is maybe I will more focus on the problem and also the motivations of the problem, and I will relatively move the technical levels down a little bit to actually make it more approachable to a wider audience. So today, what I'm going to do is actually a problem that was actually sought after a long time ago, actually, because in the time series analysis, traditionally or classically, people actually want to explore the structure of time series. That's one of the central roles in time series analysis. So let me just actually, it seems okay, yes. So let me just talk about a little history on the structural representation or approximation to stationary time series. So traditionally, time series analysis are mostly about stationary time series. So in that under the stationarity assumption, I would say stationarity is a working assumption. So under that working assumption, a lot of very classic results are derived a long time ago. Actually, there are actually big names attached to those theories. For instance, there is this Wiener-Kolmogorov prediction theory. So this theory, Wiener-Kolmogorov prediction theory, is mostly just trying to forecast the value of a time series in the future by an infinitely long past observations. So if you have a time series of infinitely long past observations and you want to forecast the time series of the immediate future, then Wiener-Kolmogorov's prediction theory basically says that there exists actually a unique linear combination of the past to forecast this future, and the byproduct of this Wiener-Kolmogorov prediction theory is also saying that a stationary time series under very mild conditions, a weakly stationary time series actually can be written as a AR infinity form, so auto-regressive time series of infinity order. So that's what Wiener-Kolmogorov's prediction theory is actually about. So that was one of the first structural representation of a time series, of a stationary time series. So after that, there is a relatively more well-known result, which is called mode decomposition. So mode decomposition is actually everywhere in all textbooks of time series analysis. So what is mode decomposition? So mode decomposition basically says that if you have a non-deterministic stationary time series, then it can be written in a MA, which means moving average, MA infinity form. So in other words, mode decomposition is another structural representation of time series where it basically says that time series can be written in a moving average form. of infinite order. So there is a significant development of Wiener-Kolmogorov prediction theory in the 1960s, where Baxter has developed something called a truncation error investigation of this AR infinity representation. What Baxter did was basically, because Wiener-Kolmogorov theory was actually nice, but it's actually not practical in the sense that it talks about what happens if you have an infinite past of the series. But in practice, we only actually get a finite length time series. So therefore, you have to investigate what happens with Wiener-Kolmogorov theory when you only have a finite past observable. And then actually what Baxter did was that if you only have a finite sample time series, then the truncation error was investigated. It turns out that as long as your time series gets longer and longer, the truncation error actually diminishes. In other words, the best prediction coefficient you got for a finite number of past is actually very close to what you can get for infinite many past, as long as your time series length is long enough. So that was actually the past developments of this area. So basically, this area was developed like a long time ago, but until now, there's not much development of this whole structural representation or approximation theory for non-stationary time series in general. The reason is that one of the major difficulty of extending those things to a non-stationary time series is because all those results, what Wiener did, what Kolmogorov did, and what Baxter did was actually based on a very complicated and profound technique of spectral theory. So basically what you do is that you first transfer your time series into the spectral domain where you do a Fourier transformation. And then you actually use properties of this Fourier transformation to prove your results that it has actually this kind of a nice AR infinity form. But unfortunately, if you have a non-stationary time series, generally speaking, you don't have a spectral density definition. So you cannot define a spectral density for a non-stationary time series in general. Or if you have certain constraints put on your time series, then you can define a non-stationary time series spectral density only locally in time. So you can define local spectral densities is possible, but global spectral density is still not possible for a non-stationary time series. So therefore, it won't be easy for us to directly generate those spectral domain methods to non-stationary time series like this kind of structural representations. Okay, so that is actually something I hope that I can actually discuss with you on how to actually how to perform structural representations for non-stationary time series. Maybe through a different angle, maybe not just spectral density type of angle. Maybe we can do that from a slightly different angle to somehow get an answer to this question. So let me talk about this setup. So this AR approximation problem for non-stationary time series, I will just summarize this problem on this slide. So on this slide, we have this problem where you have a time series xin is actually a short range dependent or short memory non-stationary time series. So with mean 0, so let's just remove the mean to make everything easier. So let's just assume it's mean 0 and it's short range dependent. And what we want to do is that we want to find a auto-regressive process yin of order p such that, so this AR process definitions like this. So yin equal to this. I hope that it will be, even though you haven't seen this before, it will be easy to understand. So this is actually you can think about this as actually a dynamic system where yin is driven by the past p observations of your time series and a arrow. So epsilon in is an arrow of the process, and this epsilon n is assumed to be a white noise sequence. So basically, white noise means that the epsilon n does not have a temporal dependence. So there's only just you see that covariance of epsilon n and epsilon j, and if I is not equal to j, is 0. So therefore, there's no temporal dependence in epsilon. So therefore, what this AR process, this yin means is that the covariance structure of this yin process is only captured in this aij coefficients. So all those aij coefficients will capture the covariance structure of this y process. So therefore, this is actually a structured model of a non-stationary time series. So if you are familiar with stationary time series literature, you will know that if this aij does not depend on I, So if your Aij only depend on J, then this YIN process is actually a classic autoregressive time series. So that will be actually stationary. But now this Yij, because it's this Aij depends on I, so therefore this actually what we call an AR coefficient is actually time varying. Therefore, you have actually a non-stationary process because this A is time varying. So what I want to hopefully establish is that hopefully we can establish the result that was listed on the last line or the second to last line in this slide, is that I hope that this YIN can actually approximate this XIN very closely. If your sample size goes to infinity and your order P goes to infinity, I hope that this can be the case. All right, so that's something I hope that I can find. So this is very close to Kolmogorov-Wiener theory, where you actually in there you have a representation of a stationary time series, but here we have an approximation of a non-stationary time series. But it's of the similar spirit of Kolmogorov-Wiener theory that we hope to establish. So before we move on to the results of this thing, actually, I hope that I can give you a few examples of why this is actually a fundamental or important problem in time series analysis. So I'll give you probably a few examples of how you can use this result in certain exploration or in certain research or real problems in time series analysis. So here is actually a few motivations. The first motivation is that if I can establish an AR approximation theory, then I can easily establish an optimal forecast or optimal linear forecast theory of non-stationary time series. So the reason is because if you have this approximation, then basically optimally forecasting X from the past is actually equivalent to optimal forecasting Y from the past of Y. So therefore, in that case, actually, we know that if you have an AR process YIN, the optimal forecasting YIN is actually very easy because we have this structure. Because of this structure, we know that the optimal best linear forecast of YIN based on its past is actually equal to this linear combination of Yij, J from 1, Yi minus J from 1 to P. So therefore, you can actually optimally forecast the X based on this just the formula here. So therefore, the optimal forecasting problem is actually doable according to this kind of representation. By the way, so the original Kolmogorov-Wiener theory was actually the motivation for Kolmogorov and Wiener to think about this problem, as I mentioned probably just at the beginning of this talk, is that they actually want to establish what is the optimal way to forecast a time series using the past information. So therefore, it's not surprising for us to see that if we can establish an AR approximation theory of the non-stationary time series, the non-stationary time series forecasting will be actually also doable from this perspective. Okay, so the second thing is that if you have an AR approximation, then you can actually do inference of non-stationary time series. Like, for instance, you can do inference of this particular example where you can do inference of non-stationary time series regression. So for instance, you have a regression like this. So Zi is your response random variable. And so you have predictors Wij's, and the predictors are assumed to be fixed in this case. So if you actually do a least squares regression of this, do a regression of this kind, then what you can actually estimate is those coefficient betas. But unfortunately, if you instead of assuming this EI, which is the error of the regression stationary, a lot of times in practice, you actually can encounter the case where this EI is actually a non-stationary time series. So a lot of times in a lot of fields nowadays, like economics or like signal processing, we see a lot of cases where these errors are not actually well behaved like stationary processes. So once you have a non-stationary process, then how to make inference of beta becomes relatively more difficult. So if you actually have this AR approximation theory, then doing this prediction will become relatively easy in the sense that what you can do is that you can first get the residual EIs. For instance, you can get the residual EI hats by the regression. And then what you can do is that you can do the AR approximation of this EI, of this residual process. So once you get the AR approximation of the residual process and you get what I wrote on at the end of this slide, which is AIJs. Once you get those AIJs, then you can actually generate a lot of versions of this time series EI where I call this EI star. So this EI star is the replica of this EI by using the same coefficients of the AR approximation of this EI. And then you actually, but you generate those arrows. You can see that I have a GI here. The GIs are the arrows generated by you. So you can use computers to generate a lot of GIs. The GIs are IID standard normal errors. So by this way, you can generate a lot of versions or a lot of replica of this EI. And then you use this, you treat those EI stars as if they were actually real data, and you plug into this regression again and again and again. So this is the essence of bootstrap. So once you use this idea of bootstrap, then you can actually get a lot of different estimates of this beta I. So this regression coefficient. Then you can use those, for instance, you can generate 1,000 or even 10,000 beta I hats using 10,000 pseudo samples. So that's what we call pseudo samples or replicas. So once you have those pseudo samples, then you can actually draw the histogram or what we call sample distribution of this beta hats using this 10,000 or 1,000 samples. So then the sampling histogram will actually represent the distribution of beta j hat in your original regression problem. So therefore, you can use this sampling distribution to make inference of this beta by this kind of bootstrap idea. So this bootstrap idea was actually used before in stationary case. In stationary case, this was called ARC bootstrap. But ARC bootstrap theory was mostly just stuck in the stationary case because we don't have a theory for this AR approximation in non-stationary case. So if we can establish a non-stationary AR approximation case, then in non-stationary time series regression, then we should be able to do this kind of bootstrap as well. So therefore, this is another use of this bootstrap of this AR approximation if we will be able to actually do it. The next thing I will talk about is actually, if you want to do an efficient estimation of non-stationary time series regression, you can also use the AR approximation theory to do that. The reason is because if the regression setting is the same, so basically EJ you have Z as a response and W as predictors. At this time, I'm not suppose that I'm interested in another problem about this regression, which is that how can I estimate those betas efficiently, so as efficient as possible. So this problem was first considered by Gauss. Actually, it's called BLUE, best linear unbiased estimator theory. So if you want to actually, we know that actually from BLUE theory, we know that if you want to actually estimate beta j efficiently, the most efficient way is to actually do a weighted regression. So, but the weights actually is the inverse of the covariance matrix of those epsilons, of those EIs. So you need to put on those weights. So now you see that the most important thing now, if you want to do actually the efficient estimation of betas, is to estimate the covariance matrix, which is n by n matrix of those arrows, EIs. So once you have a non-stationary time series, the estimation of this covariance matrix is not easy because it's a high dimensional matrix of n times n. So, but if you have an AR approximation theory to this EIs, then the covariance matrix of an AR process is actually well documented, and it's very well known how to calculate the covariance structure of an AR process. So therefore, if you actually be able to actually do an AR approximation of the EIs, then you will be able to do a best linear unbiased estimation of the regression in this case. So that is another possible application if you actually have this AR approximation theory. So the final application I want to talk about, or final motivation I want to talk about, is you can do structure inference of non-stationary time series in this case. So I just listed a few of them. So the underlying idea of why you can do the covariance structure inference of non-stationary time series using AR approximation is that, so it actually boils down to the essence of this approximation. The essence of an AR approximation is to approximate a very complicated non-stationary time series covariance structure by a simplified or a structured covariance structure of AR processes. So in other words, I would say that AR approximation in essence is a theory about approximating a unstructured covariance matrix by a structured covariance matrix. So therefore, if you can actually successfully approximate a non-stationary time series covariance structure by an AR process, then you can actually make inference. When you want to make inference of the original time series X, which is unstructured, you don't know about it, then you can actually transfer that problem to making inference of the AR process of YIN. But YIN the structure will be much easier to make inference of because it's an AR process. So it's much easier to make inference of. For instance, if you want to test whether the original time series xin is actually stationary time series or not, then what you can do is that you can test whether the aij's does not depend on I or not. So as I mentioned here in the few slides before, so here the y's are driven by aij's, but if this aij's are not dependent on I, then the y is actually a stationary process. So therefore, if you want to test the original time series is stationary or not, then you can actually transfer this problem to testing whether this aij is dependent on j or not, so dependent on I or not. So then in that case, this problem becomes actually tractable. So because it becomes a concrete mathematical problem instead of just an abstract problem of whether the original xij's covariance structure depends on time or not. It actually transfers your problem into a concrete problem of whether this aij depends on I or not. So that's much easier to handle. And also the case where you can also test whether this aij is a white noise, sorry, the original time series xij is white noise or not. So if you want to test whether this xij is white noise or not, then what you can do is that you can test whether those aij equal 0 or not for all ij's. So if these aij's are all zeros for all ij's, then that means that your xin is actually a white noise process, which means that your original xij does not contain any dependence, the temporal dependence in it. So also you can test certain parametric models of xin. So nowadays there are lots of parametric models for non-stationary time series, but model checking or model validation of these models are important. So if you actually want to do certain parametric model validation of xin, you should be able to transfer those to a corresponding thing about this y's, and then you will be able to actually do something about it, hopefully using this AR approximation theory. So that is all the actually the motivations I will talk about in terms of this AR approximations usage in time series analysis. So I would say that time series analysis, the most important thing is to develop certain theory about the dependence of this time series. A lot of times I think that time series analysis, when you investigate time series analysis, the dependence is both a curse and also a blast. The reason why it's a curse is because the problem becomes much more difficult than the problem where your data is actually independent. So a lot of things needs more complicated treatments. But why it's a blast is because actually when you do time series analysis, you will find out that temporal dependence can provide a lot of useful information about the future. So once you want to actually do a lot of nice predictions and things like this, then the temporal dependence can be, if you utilize those things very, very nicely, then you will be able to actually do things efficiently. So in my case, actually, this project, just going back to this AR approximation project, is mostly about how we can actually explore the dependent structure of time series. So if we can explore the time series dependent structure using a simplified and structured way, so that will actually give us a lot of benefit. Okay, so here towards the theory. So I will actually in this talk, we only have two assumptions. Those two assumptions are essential in the auto-regressive approximation theory, AR approximation theory. The first is that we need this time series to be actually short-range dependent, in the sense that we need that the covariance between xi plus r and xi to be actually uniformly decaying in terms of r. So, and this decaying speed is actually controlled by this tau parameter. So the larger than tau, the larger the tau, usually you have the shorter the dependence is. So usually in our theory, we need this tau is larger than 1 actually. So here we just say that tau is larger than 0. But in the theory later, I will show you, we usually need tau is larger than 1. So you need that covariance to be decaying to 0 as r goes to infinity. So the second assumption we need to make is that we need to make sure that the time series autocovariance matrix is not singular, in the sense that you need the smallest eigenvalue of the covariance matrix of x1 to xn to be larger or equal to some universal constant kappa. So this kappa is a universal constant if n is large enough. So this is basically to avoid the case where you have a covariance matrix that is nearly singular. So if you have a nearly singular covariance matrix, we know that the AR approximation won't work. So that's also the case for this classic stationary case. So for the classic stationary case, the Kolmogorov-Wiener theory also needs a condition like this. So you need that actually your covariance matrix is not singular or not near singular. Okay, so basically those are the two assumptions that we need to make in order to make sure that we have this auto-regressive approximation theory. So before we talk about the AI approximation theory, we need to actually talk about the prediction theory of non-stationary time series. The reason is because AI approximation and prediction, they are very much, I would say that they're intertwined together. They're like brothers. So they're much like the same problem, or it's sometimes. So therefore, in order to think about how the AI approximation works, it's actually nice for us to think about how the prediction works for non-stationary time series. So we talk about this one step ahead best linear predictor of any xi in the time series. So basically here we have this xi equal to a linear combination of all the paths. You can see that here the summation j is from 1 to I minus 1. So therefore your time only starts from 1. We are not, in our case, we are not assuming that we have infinite paths. We only have paths which is starting from time 1. So if you want to predict xi from all its paths, which means that that's x1 from x1 to xi minus 1, then the best linear forecast can be written like this. So the best linear forecast is a linear combination j from 1 to I minus 1, phi ij, xij minus j. And epsilon I is something we call an estimation error, so a forecasting error. The forecast error is called epsilon I. And the phi ij, they are called best linear forecast coefficients. So then actually under the assumption that I listed in the previous slide, we can actually derive this. I would say this is a very important result leading to the AI approximation. That basically talks about the decay rate of these phi ij's. It turns out that the phi ij's as a function of j will decay like this rate, log j plus 1 divided by j to the power tau minus 1 uniformly in I. So that is actually this. So this was one of the most important results for the previous Kolmogorov winner prediction theory as well. So they need also this kind of decay rates to establish their theory. But they actually developed their theory from the spectral density point of view. So they have a spectral analysis point of view. So what we have done here in order to derive this result was from actually a spectral operator theory, where you have actually a covariance operator, and we actually investigated the decay rate of the inverse of that covariance operator. So it turns out that if your covariance operator is well structured in the sense that it's actually short range dependent, then the inverse covariance operator also decays very fast off diagonally. So therefore, you can use that result to actually derive that you have this this result of decaying speed of this best linear forecast coefficients. So by the way, I forgot to actually introduce my co-authors at the beginning of today's lecture. So Xiucai Ding here is actually one of my former PhD students, and he actually now works in the States at UC Davis as an assistant professor. And there's another collaborator Yan Cui, who is also who is also working on this project, and she's now actually a postdoc with me. So previously she worked as a PhD student with me, but now she works as a postdoc with me. So those are the two major collaborators, and this talk is also based on a few papers I wrote with my students. All right, so this result is about the decay rate of those best linear forecast coefficients. So based on this result, we have a further result, which is similar to what Baxter did in the 1960s about stationary time series, is that if you actually not using the whole past to forecast the future, we instead, you see that in this equation 1, we are actually only use the B past information to forecast the future xi. So if xi is the observation you want to forecast, then the previous slide, I use all the past information, all the past observation to forecast it. But in this slide, I'm only use xi minus 1, xi minus 2 up until xi minus b to forecast xi. Instead, in other words, I'm truncating the past. I'm truncating the past to I only want to use the past b observations. So now you see that if I only use the past b observations, then the phi ij, the best linear forecast coefficient, it will be different from the previous case because I truncated it. So the previous case, the phi ij is when you use all the information, but now you only use past b information. Now the phi ij and phi ij will be different because you use different information to forecast the future. But it turns out that you can control these two differences. It turns out that the difference, the uniform in I the difference between phi ij and phi ijb can be controlled in this theorem that I established with my former student Ding, is that we have this result here. So therefore, this is actually what essentially what Baxter did in the stationary case, where he used spectral domain methods. But here we just use operator theory. So it turns out that we actually can establish this result. So so you can see that as long as B is large enough, so as long as you use sufficient number of past information to forecast the future, then forecasting using all the past information and forecasting using only the B past information doesn't make much difference. So this also depends on tau. If tau is large enough, then the B can be very small. So basically, you can see that if tau here is like, for instance, like 5, then your B can be chosen as something like n to the power 1/4 to make sure that the right-hand side is actually quite small already. So therefore, this result is actually a result about how much truncation error you will get once you only use a limited number of past to forecast the future. Okay, so that is actually what you can establish here. So based on all those results, what we can actually establish here is that you can have an AR approximation theory in the sense that you can define an ARB process like equation 2 there. So you can define an ARB process in this way, and then you will find out that this xi and yi, the difference will be, so I use the notation OL2. So basically this means that the left-hand side minus the right-hand side, the L2 norm of this difference will be of this order. So that's what it means. So you have that xi minus yi's L2 norm is of the order that's related to both B and tau. Okay, so it turns out that, so as long as your B is sufficient large, definitely the tau, the larger the better, but as long as your tau is, here you need this tau is larger than 1.5, as you can see that, because you have B to the power minus tau minus 1.5 there. So therefore, if your tau is larger than 1.5, and if your B is sufficiently large, then your xi and yi actual difference will diminish as this as B actually is large enough. So therefore, this is the result that we established that basically actually can be used as a general. I think it can be used as a general theory about how you can use a auto-regressive process to approximate a general non-stationary process. The assumption is pretty mild. Basically, we just have 2 assumptions. Therefore, actually, this theory applies to a relatively wide class of non-stationary time series. It can always, this class of non-stationary time series can always be actually approximated in this case. Okay, so that is the result, one of the major results that we got from this case. So the next thing I will talk about is somehow a practical consideration. So because the previous non-stationary time series result, non-stationary AR approximation result I got is all about a theoretical perspective. But in practice, if you want to actually apply this non-stationary Gaussian non-stationary AR approximation result, what you need is that you need to estimate those AIJs. So if you don't estimate those AIJs, you don't know how to apply it. So because in practice, you actually have to estimate those coefficients of this AR process. But unfortunately, if you don't make a further constraint about your time series, you cannot actually estimate those AIJs consistently. The reason is because there are too many of them. You see that AIJ, there are how many of AIJs? There are roughly n times B AIJs, because if you use ARB process to approximate our original time series, then the number of AIJs you have is roughly B times n. So it's much larger than your sample size. Your sample size is just n. So therefore, in order to actually consistently estimate those coefficients so that you can apply the theory in practice, what you need to do is you have to put some further constraint on the structure of the non-stationarity. Otherwise, you won't be able to do that in practice. So therefore, what I have put in this slide is that I have put one more constraint on this time series, which is called the local stationarity. So once I put this local stationarity constraint so that the AR coefficients can be estimated. So then what is local stationarity? Local stationarity is pretty simple to understand. It's basically saying this is local stationarity basically is saying that your time series, even though it's non-stationary, its non-stationary structure cannot change too abruptly over time. The non-stationarity can only evolve smoothly over time or slowly over time. So that actually controls how the temporal, the change behavior, how the temporal change, the temporally how this covariance structure actually changes over time. It cannot change abruptly like crazy. It can only change smoothly over time. So if that's the case, then we have the hope that the AIJs can be estimated efficiently and consistently. So here is the formal definition of what local stationarity is. So basically, that this local stationarity, the definition equation 5 means that at each time ti, your covariance structure, which is the covariance between xin and xjn, can be approximated by the covariance structure of a stationary time series. You see that this gamma, this gamma function, if we fix t, this gamma function at any given t is the autocovariance function of a stationary process. So therefore, this is basically saying that the covariance of xin and xjn, as long as I and j are close enough, then it's very close to the gamma structure. The gamma structure is the covariance structure of a stationary process. So therefore, the equation 5 essentially is saying that your covariance structure, as long as you are restricting yourself in a very small segment of the time series, is approximately stationary. So you have but generally in the global level, definitely your time series covariance structure changes, but it changes smoothly. So therefore, if you zoom into a very small segment of the time series, then the time series actually approximately looks stationary. So that is what this local stationarity assumption is. So this local stationary assumption basically actually can give us a very much help in terms of estimating those AIJs. So here is also a corresponding definition of those phis. Phis is just the phi t now can be defined as a continuous function of t, and which is the covariance structure of the phi treated as a matrix inverse times its own covariance structure gamma t. So this is just a technical definition of what. So because this phi t here will be, I will use this phi t here in equation 6 to approximate this phi ij here on this slide. You see that on this slide we have this best linear predictor of xi, and this phi ij is actually written on this. It turns out that if you have a local stationarity, this phi ijs can be actually approximated by a function of t, a smooth function of t. So which is here in this, which is defined in this equation 6. Okay, so here is the result. It turns out that in this case, if you have a locally stationary time series, then we have a corresponding AR approximation result like this. So the AR approximation result is more complicated in this case. So it involves basically b and tau, but also there's an extra term in equation 7, which is b to the power 2.5 divided by n. This is coming from the local stationarity approximation. So because in each local structure, we're approximating it by, in each local point of time, we're approximating it by actually a stationary AR process. So therefore, the stationarity AR process, the stationarity requirement for each local approximation will actually produce this b to the power 2.5 divided by n. We call that a extra bias of this approximation. So, and it turns out that you can see that now the phi ij becomes a phi j of time. So a phi j of time compared to phi ij is actually a very, very good simplification of the estimation problem. It's because now phis instead of phi ijs becomes a function of j. Phi j of time. As once you want to estimate a smooth function, the number of parameters you need is much less. Because if you want to estimate the phi ijs for, let's say, just fixed j, if I want to estimate the phi 1j, phi 2j up to phi nj, you need n parameters to characterize those things because there are n of them. But if you only actually estimate the phi j of t, so then a function you can actually, as long as this phi j of t is smooth enough, you can use actually a very small number of parameters to characterize a function, smooth function. Okay, a smooth function, depending on how smooth it is, can be well approximated by a basis function of very small number of bases. So therefore, you can actually reduce the dimensionality of this problem significantly if you actually do this local stationarity assumption. Okay, so now let me talk about a generalization of the problem where I talk about the locally stationary functional time series. So what is a functional time series? It's a high dimensional time series where I think in Canada, this type of things is actually one of the pioneering works in functional time series is actually conducted in Canada, where we have like in McGill, like Jim Ramsey, they have done quite a lot of work on this functional data analysis. So, but now we also in practice, a lot of times we'll encounter functional time series where you have actually ordered observations, and at each time, actually timely ordered observation, and at each time, what you observe is a function. For instance, we have a real data like this. So basically, we have observed like this kind of telecommunication downloads for a company. So at each day, we have a curve because we at each day of the observation period, we observe at each minute we observe how much download are there for the server. So therefore, we have on each day we have actually a very dense curve of how many downloads are there on the server. So therefore, what you can treat the observation for each day is that you can smooth those curves, smooth those downloads, and make it a curve. So that represents the download pattern of the server for that whole day. So therefore, for each day you have one observation, and that one observation is the download of certain applications from the server for that day. So that's a curve. So usually it peaks in the evening time at 8 p.m. and it actually goes down as people sleeps, and then goes up again in the daytime as well. So you have actually a smooth curve for each day. But now you have how many days here? We have here about actually a year of data. So that's why we have like about 300 curves. And those 300 curves are ordered in time. So therefore, if you want to actually investigate, make prediction of this time series for the next day or for the next few days, then what you need to do is, I think it's better for us to view it as a functional time series and see how we can optimally forecast this functional time series. So this second graph on the right-hand side is actually a sort of a cross-section of this left-hand side graph, which means that if you focus on a particular point, u equal to 0.2, which means that you are taking a look at something like 3 a.m. in the morning. For each day, in the 3 a.m. in the morning, you have a number of downloads, and then you think about that as for each day, and you actually collect them as a time series. Then this right-hand side time series is a time series plot of downloads for 3 a.m. for all those 300 some days. Okay, so that's what this looks like. So this is actually quite, as we actually can see that this is actually a non-stationary time series because the variability actually changes over time, and the mean definitely also changes over time for this time series. So it turns out that we can also have this locally stationary function time series definition. So it's very similar to the locally stationary time series definition previously in a few slides before. The only same difference is that now we need to actually use a stationary functional time series to approximate the original time series at each local time. So therefore, now in this definition here, the approximating time series is a functional time series at each local time instead of a scalar time series. Okay, so this is the only difference. So it turns out that, so I think I can skip this slide. So this slide is actually an example of a locally stationary functional time series from actually a system point of view. So here is actually a detailed definition of a detailed example of locally stationary time series where you can define it as a nonlinear system that's driven by some information until now. So this is actually equation 9 is a specific example of this. So I think I can probably skip this example here. So basically what we have here is that if you actually assume that you have a locally stationary functional time series, and it's also short range dependent, and you need a few more example conditions. So therefore, I just wrote in on this slide under some mild conditions. Those mild conditions contains that your time series has to be non-singular in terms of covariance operator, and it also has to be short range dependent, and also it has to be sufficiently smooth. So as long as you have those conditions, then you have that this the original time series YIU, original functional time series, can be actually approximated by a functional ARB star model. So you can see that the right-hand side is actually a functional ARB star model. So you can use a functional ARB star model to approximate the original time series YIU, and the arrow is relatively more complicated in this case. The arrow is this arrow because there's this high dimensionality going on. So that's why the result becomes more complicated. But we have to pay attention to that what this approximation arrow is involving. So basically, the approximation error involves the D1 and tau. Tau here is the temporal dependence decay rate, and the D1 here is the smoothness index of the functional time series. So basically, the smoother your functional time series is, the better you can get in terms of the approximation result. And definitely also the temporal dependence decay rate, if it's faster, then the approximation is better. So usually that's the case. So using this result, actually, I and my postdoc fellow Cui was able to actually establish a optimal forecasting theory for locally stationary functional time series. You can use this AI approximation to actually derive the optimal forecasting of this locally stationary functional time series. So that is actually the theory I want to talk about. So basically, I don't have much time left. So therefore, but the most important things are mostly done for this talk. So in this talk, the most thing that I hope that I can achieve is that I hope that I can just convey the importance of AI approximation and certain applications of it, and then what we have done so far. So now, on this slide, there is this result where basically it's actually a detailed implementation procedure of how you can do this estimation of those phi-j functions, because we need to estimate those phi-j functions in order to actually perform the aforementioned inference. So if we want to do that, then we can actually, as I just mentioned before, we can actually decompose this phi into basis functions. So you can see that this alpha k t is actually any basis. Usually what we use is actually also normal basis, but you can use any basis functions to expand this phi j t. And here you can see that I graphed two basis functions. One is actually the Chebyshev polynomial basis. The other one is actually, I forgot to write down what it is. Actually, if you are familiar with wavelet analysis, you will find out this is actually the Chebyshev wavelet with order 10. So this is actually this. So you can use actually whatever basis to expand your function. And then now, if you expand your functions, you will find out that the problem, the phi-j-t, if you want to estimate the phi-j-t, then the problem transfers to a least squares regression problem. Because if you actually combine your previous xi minus j's with those basis functions, then what you are actually estimating is this aj case in this CIF expansion. So you can see that the CIF expansion, there are actually those ajk's there in the CIF in front of the CIF basis. So now what you need to estimate is simply just those ajk's, which are the CIF coefficients. So how many are there? So it turns out that the number of CIF bases is b times c. So there's a double summation in 12, and the double space summations k from 1 to c and j from 1 to b. So therefore, there are b times c regression coefficients you need to estimate. But usually b and c are very small. They are divergent. B and c, they should diverge to infinity, but usually they diverge very slowly. For instance, the b is divergent something like n to the power 1 over 4, and c is something like n to the power 1 over 3. And if you just multiply them, the still is much less than n. The number of predictors you need, as long as you have some mild assumptions on things, it actually decays pretty. The number of predictors actually diverges very slowly. So therefore, you can actually estimate this regression no problem. So because the number of predictors is actually not that many. So then what you can do is that you can estimate this by the least squares regression, which is also a very fast way to calculating this. Then you can actually estimate this AIJs. So once you have estimated AIJs, here is a little inference problem that we did, is that we can use this estimated AIJs to make inference of the original regression, or make inference of the original prediction parameters, or whatever inference problem you have. Here is a particular problem where you actually try to test whether those fees are constant over time or not. So that's equivalent of testing that the original time series xi you observe is actually correlation stationary. So if you want to test whether the original time series is correlation stationary, you can use this test to do that. And this test boils down to a quadratic form of a high-dimensional time series of dimension b star times c. And then we have established in my paper with my former PhD student, Ding, is that we actually did a Gaussian approximation of this quadratic form. We proved that this quadratic form, this high-dimensional quadratic form, can be approximated by a high-dimensional Gaussian quadratic form. And then the Gaussian quadratic form has a central limit theorem. So that's what we established. And then you can use this central limit theorem with bootstrap to actually make inference of the original testing problem. The original testing problem was that whether the time series is correlation stationary or not. So we should be able to do that. All right, so here is some simulation results about power and also type 1 error of the testing of the constancy or testing of the correlation stationarity of the time series. So it looks okay, but yes, but it's just a simple simulation result, and those are the literature that Ding and Zhou's 2 papers are mostly about the AR approximation in the universe case. And my paper, the paper with Cui is actually just written and we just submitted it. And this one is actually about the AR approximation for functional time series. Okay, so that's pretty much I want to talk about. And I thank everybody for your attention.
Thank you very much. We have one question from the audience, and then we'll ask from the audience, from the Zoom.
Okay.
Do you see it, or do you want to?
I don't see it actually. Let me see. Oh yeah, I see one chat.
Yes.
Okay. Approximation. What is the relationship between n and p in limiting regime? Also, how do you decide on p in practice? Okay, so that's a very good question. So basically, P is actually the AR order that we need to choose. So the P's AR order, usually what we choose is that we have to actually just truncate it using to an order where after that order there's no significant dependence in the time series. Basically, AR. So basically, what we can do in practice in this is that we can actually I'm having a recent paper with Ding here in this mentioned in this talk is that we are investigating the partial autocorrelation function. That's what we call PACF in time series analysis. We are investigating the PACF of locally stationary time series. So in practice, what you can do is that you can actually investigate the PACF of non-stationary time series and see at which order the PACF actually essentially disappears, or actually essentially is not important anymore. Means that their order is their value is significantly small. If that's the case, then you can truncate your P at that order. So that's usually what we do in practice. Yeah.
Any questions from the audience? Yes, go ahead.
Yes.
It's interesting to see that if you have long memory that is tau smaller than 1, the coefficient becomes unbounded.
That's right. So if tau is less than 1, we have to actually be careful. I guess that we still can derive something, but I'm not quite sure whether this approximating order will be actually good enough for practical use or not. That's yes. So non-memory case is actually much more difficult, I would say, if tau is less than 1. Yes, it's much more difficult.
Then,
yes.
When you approximate by the AR process, you need basically tau greater than 1.
That's right. We need tau. Yeah, that's just technical reason, because the operator theory we use may not be that sharp to actually be able to control the case where tau is very small. So I would say it's probably just because of that. Yes, and also unfortunately, for the stationary case, the Kolmogorov-Wiener theory and Baxter theory, they cannot apply to like the long memory case as well. So that case for stationary case even is relatively open, I would say. Yes.
And when how your methodology is important to know that tau is greater than 2.
Yeah, you can add, yes.
How appears
you can estimate yes, that's a very good question. So for locally stationary time series, you can do that because you can estimate the covariance structure consistently. So in that case, you can actually just try to do whatever you want. For instance, you can investigate either the PACF of locally stationary time series and see whether it's decaying fast enough or not, or you can even just do the ACF of the locally stationary case, and you can see whether it's decaying fast enough or not. Either case, if you find out it's not non-memory, then you are okay to deal with this case. Yes, so that's doable in the locally stationary case, I would say. Yeah.
I have a question about the assumption 2, the minimum eigenvalue.
Yes.
I think I'm not really understand how this minimum eigenvalue assumption do not rule out the case of integrity of order 1 or 2 time series.
So even at the beginning of yes, so we have a autocorrelation. So the autocovariance matrix assumption, right?
Yes.
So that's where is it? Yeah, yes, here. Yes.
So what about integrated time series?
So if I have integrated time series, then this one will, I think this one will be violated. So the first one will be violated already. So if I have an integrated time series, then the decay rate won't be this to 0. So yes.
This framework is
Yeah.
basically for locally stationary time series.
Yes, this one is for I would say it's locally stationary. So your non-stationary can still goes very wildly. So for instance, you can have a time series where at odd numbers of time your covariance is 0.5, at even number is minus 0.5. Like this. If it's not, but it should not be integrated, because integrated time series is actually a relatively long range dependent time series. If you actually, it's even so. But anyway, you can view it as long range dependence because the covariance between xi and xj always equal to I if I times sigma square if j is larger than I. So this doesn't decay actually as and I and j actually gets more and more further from each other. The covariance doesn't decay in that unit root case. So that's definitely a further question that we can think about is that how we can distinguish this time series class versus that unit root time series class. So that's something I'm trying to do recently, but I don't think there's any result yet. But I do feel that it's doable. So we can actually, because these two time series have different scales actually. So if you think about the normalizing scale, this short range dependent time series scale is 1 over square root of n. But the long range dependent, the unit root type of time series, if you want to normalize this time series, the scale is n to the power minus 3 over 2. So they have different normalizing scales. So that using this difference in normalizing scales, we should be able to actually do like a rigorous model selection over those two time series classes. So that's basically what I think. Yeah, but I haven't done it. Yes.
Then we can continue the discussion. There is a wide-ranging reflection in the room behind. So thank you very much again.
Thank you very much.